Hello everyone! Today we'll talk about the solution of the problem map of highest peak. There are multiple approaches to solving this problem, but in particular there is a set of similar approaches that might lead to the same solution at the end, and they can start from different points. So one starting point might be that we can assign heights to different positions on our grid greedily and create just a greedy solution, and at the end convince ourselves that this greedy solution is optimal, or just send it and see that it passes all the tests. So that's one approach. Another approach would be to think about a given cell and try to come up with a condition with an absolute upper bound of the height that it can have, and then see if you can generate an assignment that reaches the upper bound for every possible cell. And the third approach is to read the set of rules and immediately see that there is a very standard matrix, a very standard grid that passes all those rules, and so it's probably just the solution. And that grid is of course just the grid of distance to the nearest water cell. It passes of course all the rules. The distance cannot be negative, the distance from a water cell to the nearest water cell is 0, and of course that distance cannot change by more than 1 when looking at neighbors. Because if one neighbor has a distance that's longer than the other's distance by more than 1, it's a contradiction, because instead we could start at the highest distance, higher distance of the two, go to the one with lower distance and continue from there, and that would mean that the distance is the lower distance plus 1. So this is a contradiction. So the map of distance from the nearest water cell is indeed a solution to this problem, or at least one of the solutions. And of course, it passes all those rules. So we might immediately guess. And to prove it, that's the second way of solving this problem that I mentioned from the three ways, is to think about what is the upper bound for the value in our final height array. And that upper bound is exactly the distance from the cell to the nearest water cell. That's because we can get, of course, to have as high a value as possible, we have to have a difference of at most 1 between neighboring cells, which means that if the shortest path from a given cell to a water cell is equal to d, then of course the height of the water cell that can be reached by that path of d steps is 0. And since that path exists from the water cell to us, and it has only d steps, then we can only gain at most 1 by every step until we reach our node. So that node cannot have a height higher than d, because otherwise that path would have a contradiction along it. And of course it's possible to generate a grid that gives this upper bound for every possible position simultaneously. It's just the height map that is just the map of distances from every cell to the nearest water cell. So this is just a standard problem which we can solve using a BFS starting from every water cell simultaneously. So we have some boilerplate, height, width, standard, changes in rows, changes in columns, so all the directions, all the possible cardinal directions, set of visited nodes, and a queue. In Python, of course, we use a deck to hold all the nodes that we'll be visiting. And now we start for every row or column. If in that position we have water, we add it to the visited set and add it to the queue. The final result will be a separate two-dimensional list. The starting height is 0, and now we can go over all the possible positions. So, one way of writing BFS, which I prefer, is to use this walrus operator here. So, we take the length of our queue, assign it to the variable s. If it's 0, we don't do anything, we just break out of the while loop. Otherwise, we remember that the current length of queue is s, and this is the whole next layer. So first we start with water cells, then we start with cells that are neighboring water cells, and so on. And we go through all of them. So we don't care about this index in range s. So we eat up s next values in the queue. So we take the row and column that's on the left of the queue, we assign its height, so we start with 0, and after every step of this while loop we increase height by 1 because we go to the next layer. We look at all the directions, so change in row, change in column, that gives us the new row, new column. We check if they are within bounds, if not we continue. So if not we continue. If it's visited, we also continue, otherwise we marked it as visited and add it to the queue. And at the end we just return the result, which is this array that we've been populating with the heights at this position, right? So again, this way of writing a BFS is layer by layer. Just at every step, when we increase the height, we remember the size of that layer and we eat exactly as many elements from the left, so from the front of the queue.